Welcome to clickmyproject.com.
Now we discuss about the product for low complexity, low latency architecture for matching of data encoded with hard systematic error correcting codes. Next we see the abstract for the product. Data comparison is widely used to computing system to perform many operations such as the tag matching in a cache memory and a virtual to physical address translation in a translation lookaside buffer. Because of search prevalence, it is important to implement the compression circuit with low hardware complexity. Besides, data comparison usually resides in a critical path of components that are devised into increase the system performance. Example for cache and TLBs, whose output determine to flow of succeeding operations in a pipeline. The circuit therefore must be designed to have low latency as possible, or the components will be disconfused from serving as accelerations and overall performance of the whole system would be severely determined. As a recent computers employs error correcting codes to perfect the data and improve the reliability and completed decoding procedure, which must proceed the data comparison, enlarging the critical path and executes the complexity overhead. A new architecture for matching the data produced within the error correcting code is presented in this brief to reduce the latency and complexity level. Besides on the fact that the code word on error correcting codes is usually represented in a systematic form of consisting the raw data and the parity information generated by encoding. The proposed architecture parallels the comparison of data and that the parity information to further reduce the latency and complexity level. In addition, a new butterfly formed weighted accumulator is proposed for the efficient computation of Hamming distance. Grounded and butterfly weighted accumulator, the proposed architecture examines whether the incoming data matches or mismatch and the faulting conditions to store the data and certain number of error bits are corrected. Next, we see the flow diagram for the product. First, the input data to be encoded for encoding architecture. The encoding bits to be processed in two steps. First of all, the code generating process, and second to the code retrieving process. The code generating process mainly used to the XOR bank architecture. The code retrieving process is placed for the XOR bank 2 architecture. The XOR bank architecture, the encoding bits to be generate the Hamming distance based code generating process and the code to apply the XOR bank 2 process, then the encoder bit and the code bit to apply the XOR bank 2 and to retrieve the original data bits. Thus the data bits to apply the butterfly formed weighted accumulator. This architecture mainly to consider the two consist of blocks, tag and parity bit block, and the tag block to count the number of ones for XOR bank 1 architecture, and the parity bit block to count the number of ones for XOR bank 2 architecture. That the butterfly weighted accumulator mainly used to do number of ones adding the process. This process mainly consists the more number of half-adder architecture block. The butterfly weighted accumulator results is applied to the decision unit architecture. The decision unit architecture mainly considered for the some architecture process. These architecture results are applied to the table functions. This table are match or mismatch or fault condition for the data encoding processing result. This block to consider the error correcting updation block. Then the error correcting results is applied to the decoding architecture. Thus the decoding architecture to decode and compare the process, then to retrieve the original input data bit for the recoding process, then to calculate the synthesis and simulation results for our the data encode for low complexity, low latency architecture. Our optimization process is mainly for XOR bank and XOR banks architecture. This XOR gate is number of gate to 5 gates, and we implement the 4 gate for XOR bank architecture. So we optimize the low complexity for our the data encoding architecture and to reduce the low latency for our the data decoding process. Next we see the output for the product. Then open the Xilinx ISC project for our data encoding architecture. Then select the simulation process and to select the main RTL functions. Then to double click the simulate behavioral model. This behavioral model to create the iSIM project navigator. This navigator is mainly used to the simulation of the data encoding process. Then the data encoding process to apply the input data bits and to encode the output data and to create the output decode the output data bit for the same data encoding bits. The 16-bit data to input for the data encoding architecture to apply the binary input data for the any of the data encoding process and to apply the data encoding process, then to run for time specified on the toolbar. This the input data to apply the encode data, then to create the decoding data. The decoding data and the encoding data input data to be same for the simulation process. The QRST UV signal input for used to the match, mismatch and fault analysis decision unit output results. Then to close the simulation process, we open the implementation results. The implementation to open the RTL diagrammatic representation for our architecture. The RTL IC to double click the overall IC architecture. These architecture to represent see what are the logical blocks based in our data encoding architecture. Then to create the technology diagram, add and create the schematic. The technology diagram is represent to what are the lookup table, wire connections and bounded input output, then flip-flop pairs. This technology diagram mainly based on the area representation of overall data encoding architecture. Then to open the design summary process, the design summary process to create the synthesis report. These reports to calculate the device utilization in our data encoding architecture process and to calculate the timing summary for our the data encoding architecture. The maximum input time before clock and after clock timing used to calculate the latency level of data encoding process in our data encoding architecture.